Hey guys, I'm Bout of Math, and today I'll be showing you the basics of sinusoidal functions. So here I've drawn out a portion of the unit circle, right, missing some of the smaller angles, and we have our sine and cosine graphs. And we're going to look at our sine graph first. If you don't know how to do the unit circle, right, and figure out the values associated with them, I'll have a link posted in my description to my tutorial on how to fully write the unit circle. Right, so let's look at the sine function. The sine function starts off at 0 and goes up until it reaches this point here at pi over 2, and then comes back down all the way until 3 pi over 2, and then goes back up. And then it'll continue this pattern over and over and over. So we can actually see this pattern by using our unit circle, right? At 0, sine of 0 is 0 right here, and then as it moves up on the unit circle at pi over 2, sine of pi over 2 is 1, which is where we see its maximum, and then it drops as we continue seeing on the unit circle where it starts to decrease, and then increase again. So that's how we get our sine function to look like this. Now, an important thing to remember is that both of these functions that I'm going to cover are called sinusoidal functions, which is what this video is about. And this means that they have the characteristics of a sine function. So what are the characteristics of a sine function? Well, we can see its midline, amplitude, period, and frequency today. The midline and the amplitude kind of go hand in hand. So we're going to try to find the midline and the amplitude of this sine function. Now the midline is just the middle, like the horizontal line that cuts through the middle of our function. So if we were to flip our function like that, where would be the middle line? Now obviously you could tell it's at 0, but the other way to tell where our midline is we take our maximum value, which is 1, that occurs over here, and our minimum value, which is -1, which occurs right here, and then we're going to find the average between the two. So the average would be, we have two terms, so we will divide by 2. 1 plus -1 is 0, divided by 2 is just 0. So our midline, we just verified, is at y equals 0. Now what is our amplitude? Our amplitude is just the distance from the midline to either the maximum or the minimum of our function. So the distance from 0 to -1 is just 1. And the distance from 0 to 1 is also 1. So we can say that our amplitude is 1. And the amplitude kind of tells us how intense our function is. So now we're going to see our period and our frequency. Now the period is a very important concept in trigonometry, and the period of this sine function can be determined by seeing how long does it take to complete one pattern. So as I noted before, the sine function will continue onward with the same pattern. How long is one of those patterns, or oscillations as they're called? So we start at 0, we go up, and then we go down, then we go up again to 0. And we're going to continue going up, down, and up. So it took from 0 to 2 pi in order to complete this one pattern, right? And we can actually review that on our unit circle. From 0, we see that sine again goes up and then down. It approaches back to 0, but when it goes back to 0, it starts to go down. It doesn't start going up again, which means that it's not repeating the same pattern. So it goes down, and then it starts going up again until it reaches 2 pi. So we saw from 0 to 2 pi, we had one pattern or oscillation of the sine function. So I can say that the period here is 2 pi. And then the frequency is very easy to determine, because the frequency is just the reciprocal of the period. So we just put 1 over the period, which is 2 pi. So 1 over 2 pi is our frequency, making period and frequency inversely proportional. Now let's look at our cosine graph. Now I'm not the best artist, but the cosine graph looks something like this. And it starts at 1 and it dips down to -1 at pi. right? Starts at 1 and dips down to -1 at pi. And then it comes back up, so at 2 pi, it's back at 1 and ready to fall down again. So again, let's look for our midline. We have -1 and 1, right, as our minimum and maximum. So our midline has to be 0, just like we saw here. So y equals 0 is our midline. And then, similarly to the sine function, our amplitude is also going to be 1. Because the distance from 0 to 1 or 0 to -1 is 1. And then our period, well, as we noted, the cosine function is going to go down, 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 up, and then back down and up. So it takes from 0 to 2 pi, just like the sine function, to repeat an oscillation. Which means that our frequency will also be 1 over 2 pi. So these characteristics of sine and cosine, you'll see, are literally the same. And we're going to see why in a moment. But this is essentially why these two functions are called sinusoidal functions, because they behave like the sine function. So now I'll show you how we can alter these functions and what it means to alter them. So here we have a graph of a sinusoidal function, and we're actually going to try to figure out what is that function. And here we have some rules about these transformations that occur in the function. So if we have a graph of sine, and this works for cosine as well, we can alter the function using any one of these parameters. So if we alter the a value here, which goes right at the start of the function, we are altering the amplitude. So originally our a value was 1, our amplitude was 1, which meant that we just had a 1 here on the original sine function. Our b value is when we divide 2 pi over the period of our function. Right, when we had the period of our function, the period was 2 pi. So 2 pi divided by 2 pi was 1, which is why we had 1 on our original sine function. We can also use that b is equal to 2 pi times the frequency in order to find our b value. Now the c value, you have to look at the graph for, and it's our horizontal shift or our phase shift. Since we know for sure that this is a sine function, so I'll write it here, sine. We know that sine has to start at the midline, right? The 0. So if it starts at the midline, then there was no horizontal shift or phase shift. And then d is the vertical shift, which basically says how much did the midline itself move. And how we can find this is we take our amplitude, and then we just see, we take our amplitude and we can find how much the amplitude differs from the maximum value of our function. So let's start to look at our function here. Our a value and our d value go hand in hand because there's the amplitude and how much the midline has shifted. So our midline is right around here. And I know I didn't mark it, but this is 1/2, 0.5. So our midline is going to be at y equals 1/2. And how do I know this? Well, we take our maximum value, we add it with our minimum value, and we divide it by 2 to find the average. 1 plus -2 is -1 divided by 2. Sorry, I said 1/2, I meant -1/2. So -1/2 is our midline. So this is y equals -1/2. Which means that if on the typical sine function, the midline is at y equals 0, we've had a vertical shift of -1/2, so 1/2 units downward. So our d value is going to be -1/2. And then to look at our a value, we have to see how much does the function deviate from the midline. We can see that it goes from -1/2 to 1, that's 3/2, and it goes from -1/2 to -2 over here, that's also 3/2. So our a value is going to be 3/2, because that is our amplitude. And now we can find our b value really easy. Let's first find the period of our function. So I'll write it as p, our period, we start here, we go up, we go down, and we come back here. So at pi is when we have completed one oscillation, because then it continues like that, and then 2 pi, we've completed 2 oscillations. So at pi is when one oscillation has been completed, so our period has to be pi. Which means that in our b value, we have to divide 2 pi over the period, which is pi. So our b value is going to be 2. And then how do we find our c value? We have to see how much it's deviated. So where's the start of our oscillation? It's actually a 0. And it continues, at pi, whatever, but it starts at 0. Which means that our phase shift is actually going to be 0. Because just like on the original sine function, we started at the midline. So now that we have all of our parameters, I'm going to plug this into my function over here. Our a is 3 over 2. Sine of our b value was 2. And then our variable, here we have x, but here our variable is theta. So I'm going to write 2 theta. And then our c value is 0, so I'm not going to write plus 0. I'll just close it off. And then our d value is going to be negative 1/2. Okay, now let's take a look at a different example that will kind of show us the relationship between sine and cosine. So let's take a look at this sinusoidal function. Here we're given that this is a sine graph, and we want to find out what our function actually is. So let's start by looking at our a and d values. Where is the midline of our graph? So we know that our maximum and our minimum points, our values, are 1 and negative 1, which means that our average will come out to 0. So that our midline is at y equals 0. That's our midline. Right across here, which means that this is the same as the original sine and cosine functions that we saw, where the midline was also at y equals 0. So when I put d, how much did the midline shift from 0? It shifted nothing, so I put 0. What about our a value, the amplitude? Well, from 0 to 1 or 0 to negative 1, the distance is 1. So that'll just be 1. And then we're left with the b and c value. Here, our period, we see it comes down and then back up to 1, and it's going to come back down, back up, back down, back up. So this is, our b value is going to be the period on the bottom, and then on the top of the fraction we'll have 2 pi. So 2 pi divided by the period, 2 pi over 2 pi is just 1. So we notice a is 1, b is 1, and d is 0. So it's kind of looking like a normal sine function. However, when we looked at our original sine function, the sine of theta, it didn't look like this. And we're going to see that now with our c value. So the sine function originally starts where? At 0. Sine of 0 is 0. But when we look here at our sine function, and remember this is sine, we're starting at 1. But it's not that our midline has changed. It has to be that the graph has gone horizontally. There's a phase shift. So when is it 0 is my question. Well, if we see here, it's 0 at 3 pi over 2. And also at pi over 2. But we know with sine that sine actually starts going upward, not downward, right? The graph of sine was something like, so it has to start going upward and then downward. Now, if I were to extend here, over here, right, into the negative, around here, when it reaches 0 and it starts going upward and downward and back up, this would be negative pi over 2, because the period is 2 pi, right? So if the period is 2 pi, from negative pi over 2 to 3 pi over 2, we have 1 period. And so what we notice is that the sine function may actually be starting here at negative pi over 2. Or like it has shifted, either you can say negative pi over 2 or 3 pi over 2. But for the case of this example, I'm going to say that the sine function has been horizontally shifted to negative 3 pi over 2. So what I'm going to write here is negative sorry, not negative 3 power 2, negative power 2. So negative power 2. And then when we write down our function, we're going to write 1 for the a, so nothing there. 1 for the b, so nothing on b, so we're going to have theta. And then our c value is minus pi over 2. And then plus 0, so I'm not going to write that. So this is our function right here, with just a phase shift. Now, if you remember from the cosine function, this is actually the original cosine function. This is equal to cosine of theta. So what do we notice between sine and cosine? This is called the cofunction idea. It's basically that sine of theta minus pi over 2 is equal to cosine of theta. And that if you were to shift cosine, right, if you were to shift this entire equation pi over 2 here, then it would start at sine of pi, it would start at sine of theta, right, sine of 0 right here. It would be over here. So, excuse me, let me rephrase that. If we were to shift this function pi over 2, right, to the right, then this would go over here. We would start at 0, and then this 1 would be over here. And then it would look much more like the sine graph we have over here. So we can say that sine of theta minus pi over 2 is equal to cosine theta, and that cosine of theta plus pi over 2 equals sine theta. And this is the cofunction identity for sine and cosine, where if you subtract minus pi over 2 or add pi over 2 on the phase shifts of these respective functions, you'll get their cofunction identity, right? So that's really interesting because it kind of shows that sine and cosine are essentially the same function, just at different times. So yeah, let's look at one more example. So here we have a much different problem from what we've been working on typically, and what we can see here is that we have a clock in this scenario, and what we're going to be doing is defining the height of the tip of the minute hand using our function, our graph, our measurements. So the minute hand we have is 8 inches. The length of the minute hand is 8 inches. So from the center to where it ends, 8 inches. And then the center of the clock, so right here, is 120 inches off of the ground. Which means that if it's 120 inches off the ground, plus the minute hand being 8 inches, that means when it's pointing at the 12, the total distance from the tip of the minute hand to the floor is going to be 128 inches. And that's what happens here when time is 0. So when 0 seconds have passed by, so the start of this scenario, the minute hand is pointing at 12, which means that the minute hand currently has a height of 128 inches. We also have to note that the minute hand is not working properly, which means that it's moving twice as fast as it normally should. Now a minute hand typically takes 60 minutes to go around the clock once, but this means that at time equals 30 minutes, the minute hand is at 12 again. So instead of 60 minutes, it took 30 minutes, which made it twice as fast. So now let's take a look at what they're asking for here. Let's think about the period first. How long does it take to perform one oscillation, one pattern? Well, the pattern is just going around in the circle in the clock. Or we can also look here, it goes from here to here, but we don't have any units on this graph here. We're actually going to fill in the graph ourselves. So we can tell from the clock that it would take about, or not about, but exactly 30 minutes in order to go around the clock. So that's our period. Our frequency is going to be the reciprocal of our period, so that's 1 over 30. And then our amplitude. Now, let's look at our midline first. Our midline is going to be 120 inches. Why? Because the minute hand is going around that 120 inches, right? It's going to be either 128 inches, which it is at the start, or once it's pointing down at the 6, it's going to reach a minimum value, right? It'll be 120 inches minus 8 inches because it's going further down to the ground. So that'll be 112 inches, right? And so this is kind of our interval of the values, right? This is the range of our function of where the minute, how tall the tip of the minute hand is in comparison to the floor. And we see here there's a difference of 16 between these two. So 16 divided by 2 is 8, and then it deviates 8 from the midline, which is 120. So our midline is 120, and it deviates 8. That means our amplitude has to be 8. So basically, that's how we know where the midline and the amplitude is based off the clock going around. Now here we have a graph, and we're going to plot some points. So the first point I'm going to plot is when time is 0, because it tells us the minute hand is at 12, so that means the y value, my height, will be 128. So I'll name these axes. This x value will be time in minutes, and this y-axis will be the height in inches. So let's see. Our midline here is actually already dotted over here, and it shows us that our midline is 120. So I'm going to say that this point up here is going to be the start of our scenario. So 0, comma, and then we're going to put here the maximum point, which is 128. 128. And this means that over here, after one entire oscillation, it's past 30 minutes. So I'm going to put here 30, comma, 128. Because we have 30 minutes that have passed, and it's back at 128 inches, the minute hand. Now, let's see what happens here when it reaches the midline. Well, it reaches the midline when the minute hand is pointing at 3, right? The minute hand is level with the center of the clock in terms of the vertical position. So this over here is going to be, typically it takes 15 minutes to reach for the minute hand to reach the 3. But because it's moving twice as fast, it's only going to take half that amount of time. So instead of 15 minutes, it'll take 7.5 minutes. I'm going to write 7.5, comma 120. Which means that it'll take a total of 15 minutes to reach the 6, right? And when it reaches the 6, we actually get our minimum, right, which is the 112. So we'll get 15, comma 112. And we can continue at 22.5 minutes. We'll have reached the 9, which again makes it level with the center of the clock. So we'll have a height of 120, right, which is level with the midline. And then again, after we do a full rotation back at 37.5, we have 120, and then so on and so forth. So you can just continue marking these points here, but I'll just leave it as is, because as we know, all sinusoidal functions are periodic, meaning that they'll repeat in pattern. Now, finally, we're going to look at two intervals where the graph is both decreasing and concave up. Well, let's see. Concave up means it's U-shaped, so like that. So if it looks like this, it's wrong already. So let's see, where is a U-shaped? U-shaped here, and U-shaped here. So we have our two intervals already. So let me see now. It says decreasing as well. So decreasing has to go down. So it has to be this part of the graph, where it's going down like that. I can see that here from 7.5 to 15, the graph is going down just as noted here. So I'm going to put that as my first interval. 7.5, 15. And then for my second interval, I see it again here at 37.5. Well, I know it takes 7.5 minutes to go down to the minimum value. So I'll put here, this is 45, comma, 112. And from 37.5 to 45, we have that same pattern that occurs from 7.5 to 15. So this makes our second interval. How fun. So what can we take away from what we've learned today? Well, we know that sinusoidal functions are periodic and oscillatory, meaning that their patterns repeat and they behave like sine functions. And here we have the list of how to transform these sinusoidal functions. Remember, they apply to both the sine and cosine functions. And we also have the list of cofunction identities, which say that sine of pi over 2 minus theta equals cosine of theta, and cosine of pi over 2 minus theta is sine of theta. Now I know I covered it a bit differently, but this is the proper identities. You can also obviously try to play with the graphs of sine and cosine to find other ways to rewrite these identities. But these are the main ones that are associated with the sine and cosine cofunction identities. So yeah, those are the basics of sinusoidal functions.